Okay. So the last one we have to do then is the nonsense mutation. So definition here would be when a mutation causes a premature stop codon, which is going to shorten our polypeptide. When a mutation causes a premature stop codon, shortening the polypeptide. So here we are going to be impacting the polypeptide. The protein is not going to be functional. This is one of the worst mutations you can have because you don't even have the opportunity of the R groups being similar between the amino acids that are put in, like you do in the missense. Here you just have, it's called a truncated protein, so it's shorter, it's broken off. Okay, so we will perform here a substitution on, let's see, this cytosine right here, so where it goes CGT, we're going to substitute this C right here, this cytosine. Okay. So let's go ahead and put in our mutation now. Everything else is going to be the same. We are going to substitute it with a thymine. So that C is becoming a T. Okay, so just like yesterday, we will then transcribe it and then translate it. So our original strand is going to be the same as it was the whole time yesterday, because I just used the exact same exon through this whole thing. So if you just look back up at the missense or silent mutations, you're going to have the same combo of stuff. So the AUG is still there. That's going to code for methionine. That is our start codon. Then we have UGG, which is tryptophan. CAC, which is histidine. And then finally UGA, which is that stop codon. Puts in the release factor, ribosome breaks off of the messenger RNA, translation stops. Okay, but if we then were to transcribe the mutated strand, we still have, so TAC, we still have the AUG. So that still gets us to methionine. Okay. Then we have ACT instead of ACC, so that would go to UGA. What does UGA code for? Stop. Oh, I should have done that in purple. Okay, so there is our shortening, our truncation of the polypeptide. We were supposed to have methionine, tryptophan, histidine. We now just have a methionine that shortens the polypeptide. We're not going to have a functional protein at this point. So nonsense mutations will always cause a polypeptide to not be functional. Missense mutations typically will. In very rare instances, like if you get a polar R group substituted for another polar R group, the protein might maintain its functionality. It just kind of depends on what you end up with. Silent mutations, you always maintain functionality because you don't get a difference in the polypeptide sequence. So these are the 3 different mutations that we see at the level of the polypeptide itself. This is where the consequence actually comes in. If the mutation at the DNA level or at the RNA level does not cause a difference in the polypeptide sequence, then the mutation really doesn't have any impact. Does that make sense? That is the end of this.